Good afternoon, ladies and gentlemen. My name is Grigory Slinkov, and today I would like to tell you about the basic principles of the mode locking technique. To be specific, you will learn about active mode locking and its frequency modulation and amplitude modulation implementations. The mode locking technique allows to obtain an evenly spaced train of short and powerful pulses, the so-called ultra-short pulses, from a conventional continuous wave laser. It is worth noting that the ultrashort pulses should not be mistaken with the so-called compressed pulses, obtained via chopped pulse amplification, which won the Nobel Prize of 2018. Chopped pulse amplification involves successive stretching, amplification, and compression of an already emitted laser pulse, while mode locking concerns the process of pulse emission itself. We will begin our analysis by considering the scheme of a conventional laser. Its principal components are the gain medium, providing a two-level system, the pumping element, providing inverse population for the two-level system, and the optical cavity, also referred to as an optical resonator. The cavity is basically a pair of high reflecting mirrors confining the light inside of the gain medium. This way, the radiation spectrum of a laser will be composed of a broad emission band of the gain medium and a series of narrow peaks corresponding to the longitudinal modes of the optical cavity. In a time domain, we can present this radiation as a sum of terms corresponding to individual optical modes. Each of these modes has its own amplitude given by the curvature of the gain medium spectrum and its own frequency corresponding to the mode number. We should note that the spectral distance separating the neighboring modes is constant and is proportional to the speed of light and inversely proportional to the cavity length. In the absence of mode locking, the phases of the modes are independent of each other, which results in a seemingly random variations of the intensity output. However, it can be seen from the animation that as we gradually reduce the phase difference between the modes, the intensity output takes a form of a short and powerful pulse. This transformation is the essence of the mode locking. Now, we have seen that the mode locking occurs when the phases of the laser modes are equal, which can be understood as all the modes emitting light simultaneously. If the mode locking condition is satisfied, the output radiation expression takes a simple form presented in this slide. From this formula, it readily follows that the peak intensity of the light is proportional to n squared and the width of the pulse is inversely proportional to n, where n is the number of locked modes. In order to make modes emit light simultaneously, to lock them, one has to provide them with some sort of a mechanism of acting upon each other. As we know, amplitude modulation of a signal with central frequency omega creates two sidebands, one with upshifted central frequency and one with downshifted central frequency, where capital omega is the modulation frequency. At the same time, both sidebands will bear original signal's phase. If we place an amplitude modulator inside the laser cavity and set the modulation frequency equal to the spectral distance between the cavity modes, the sidebands of each peak will coincide with the adjacent peaks. The sideband radiation will now take part in another mode's process of stimulated emission, but will still bear the phase of their parent mode. Since every mode will have such sidebands, this will eventually lead to all of the modes emitting light simultaneously. The modes will be locked. This approach, of course, poses significant limitations on the transparency of the utilized modulator, since high insertion loss may disrupt the stimulated emission process. Because of their ability to provide modulation when driven by a non-modulated signal, most commonly used are Acasta optic modulators operating in a standing wave mode, in contrast with running wave modulators. Another way of creating a frequency-shifted sideband is frequency modulation. Unfortunately, devices providing direct frequency modulation, such as Acasta optic frequency shifters, are usually impractical for a number of reasons. Instead, electro-optical phase modulators are used. It is obvious that simple introduction of a phase-shifted component cannot result in appearance of a separate spectral component. However, if the added phase shift is linearly dependent on time, we can see after regrouping the terms that the result will be effectively frequency shifted. This is it for today. Thank you for your attention. I hope you enjoyed this video. Next time we will discuss passive mode locking and other ultra-short pulse techniques, including Q switching and cavity damping. If you have any questions, please feel free to ask them in the comments below.